Alright, welcome to the third and final part of the equilibrium, balance and levers section, where we're dealing with various worked examples. In this example, we've got an individual standing and he's about to initiate a heel raise or a calf raise. Um, and the question is how much muscle force is required in order to keep that equilibrium position. So in other words, to not get him to rotate down and not get him to rotate up, just to kind of keep it statically balanced. So pretend for a minute that he was standing on the edge of a step. And he's trying to keep that specific position. What makes this one different to the previous example is that we're not dealing with the mass of the foot at all. In essence, in this scenario, what we're dealing with is the center of mass of the body. So in essence, if I just draw a vertical line down, I've just magnified this region over here, and we've used basically like super X-ray vision to kind of get the anatomy and therefore study the biomechanics a little bit more carefully. Just pretend that the center of mass, weight force over here, which I'll just call FB, is acting just anterior to the ankle joint. The individual will be pivoting around the forefoot, right? That'll act as your axis of rotation, and we're still interested in the muscle force that's required to maintain that position, right? So in this case, it's your gastroc soleus complex that will create an upwards force, and we'll just call that Fm. So as always, we got to get some distances, the distance of the force relative to the axis of rotation. In this case, we're dealing with the body mass of the individual still being 70 kilograms, same as it's been throughout. In this instant, again, we've got to find what is the distance between the weight force of the center of mass. Let me just try and get that drawn in over here. So remember, it's the perpendicular distance of the force relative to the axis of rotation, which is this distance over here, which we call d2. And in this case, what would be the easiest is, yes, we could figure out the perpendicular distance from this force to the axis of rotation, or we can just look at the vertical component to make that a little bit easier. So in essence, remember we said that there's different ways to solve. So in essence, what we have here is just, we'll take this muscle force, and it's only the perpendicular component of this to the axis of rotation that will cause any kind, or create kind of any kind of torque, right? So again, if I just tend to extend that a little bit further down, and it's the distance that is to the axis of rotation. Alright, so we'll call that d1, and this vertical component we'll call fm and y. And the thing that I forgot to add in here is just to say that this force is obviously acting at some angle. We'll call that theta for now. So let's just give you some of the information. So theta, the angle at which this gastroc soleus muscle complex is pulling, is given as 80 degrees. D1 in this particular scenario is given as 20 centimeters. That's not unreasonable. D2 over here, which is the weight force of the center of mass, is given as 8 centimeters. And yeah, I think that's pretty much all you guys need. You've got the body mass, and that's it. Alright, so as always, we've got to divide this into which components create clockwise and anti-clockwise motions. So again, just denote your axes and which directions are going to be given or ascribed a positive value. So what you'll see is, if this is your axis of rotation, we have to find the sum of all anti-clockwise moments and equate them to the sum of all the clockwise moments, because if these are equal, then the condition of equilibrium is met. Alright, so if you see the weight force is acting down, if you're using the right hand rule, we realize that that would create an anti-clockwise moment. So in this case, if I just put the forces times the distance in here, so the force of the weight multiplied by d2 must equal, and therefore by implication the muscle force must create a clockwise moment, which we can see over here. Again, right hand rule, curl fingers in the direction of the force, and that will give you the direction of that rotation, and that's going to be Fmy multiplied by its distance. Sorry, that's not d2, that's d1. Alright, therefore, since we're trying to find out what that component is, Fmy is going to be equal to Fw multiplied by d2 divided by d1. So now it's just a case of plugging in some values. Alright, because remember, at the end of the day, we're still trying to find Fm, right? So we're not there yet. We're going to be finding Fmy, and then from that we'll be able to get Fm. Alright, so Fw is 70 multiplied by 9.81. Remember, it's the full body weight. And I think the thing that I have to add to this is the fact that the person's going to be standing on one leg. So I should probably just draw that in here. So in essence, the person is just standing on one leg. So all the weight is being concentrated on that one leg. It's not sharing it equally over both legs, right? So yeah, I should have just put that in there. And I'll multiply that by its distance to the axis of rotation, which we said was 8 centimeters. Remember, you have to show conversion, so 8 centimeters multiplied by 1 meter over 100 centimeters. That's your conversion over there. So that's going to equal 0.08 meters. Right? So that's all of this top part over here. I'm just going to divide that by d1, which we said was 20 centimeters. So again, you have to convert it. 20 centimeters multiplied by 1 meter per 100 centimeters, and all of that is going to be 0.2 meters, right? So once I've chucked all of that stuff in, I will get a specific value, which I just have to quickly calculate. So if I do 70 times 9.81, and I multiply that by 0.08, and I divide all of that by 0.2, I get that Fmy is equal to 274.68. And remember, that's in newtons, right? But we're not quite done yet. In essence, remember that Fmy, if I again just draw this triangle over here, if I divide this Fm value into a triangle, which I'm just redraw over here, so that's Fm, and we said that it's acting at an angle theta. Remember, any force, because it's a vector, can be given or divided into its component parts. So there's a component to the right and there's a component going up. So remember, that's going to be Fmy, and this is going to be Fmx. But Fmy is going to be equal to Fm times the sine of the angle. So I'm just going to use that convention to replace this over here. Since Fm is what we're trying to find, Fm sine of the angle is going to be equal to 274.68, and therefore Fm, and if I know what the angle is, it's just over here, is going to be 274.68 divided by the sine of 80, and I should get some kind of a value which gives me 278.88 newtons, and that is the final answer. So Fm was one of the things I was trying to find, and as with all the other ones, what is the mechanical advantage of this particular system? So let me just choose a slightly different color over here. So remember, mechanical advantage is the force moment arm divided by the resistance moment arm. which in this case the force moment arm is 0.2 divided by the resistance moment arm, which was 0.08, and therefore the mechanical advantage is 2.5, which is clearly greater than 1.0, and it therefore in this case favors the force, right? In other words, I have to produce a lot less force than what the actual body weight was. Remember, I only had to, in order to hold this position, produce 278, approximately 279 newtons, when the body weight is going to be something like 676 odd-ish, around about there, right? So in essence, I have to produce 2.5 times less force than what I weigh, which is one of the reasons why you can lift so much weight with your ankle joint, right? Purely because of the fact that the muscle is a much greater distance from the pivot point than what the actual weight force is. So in terms of lever types, remember again, I've got a pivot point, and in this case, the resistance arm is closer and the force arm is further away. So this is a wheelbarrow lever, or a second class lever system, which we also refer to as the wheelbarrow lever. Alright, so hopefully all those examples have made sense and you can see the process of calculating. You should be able to, again, apply these techniques to any given example. So you always got to look at where's the resistance force, where's the muscle force, and where's the pivot point. Then find the perpendicular distances of the force to the pivot point, right? It's literally as straightforward as that, and you'll be given most of the information as I've done so far. And that's pretty much it. Alright, catch you guys on the outside.